Hey guys, welcome to the OneClass channel. My name is Sydney and I'm currently a third year engineering student. Today we'll be going over some commonly asked math questions at both the high school and university level. If you need some additional homework help or tutoring, please check out the links in the description below. And we can get started. Okay, so our first question asks, what is an additive inverse? Okay, so it gives a description here that's saying the additive inverse of a given number is another number that is, when added, will give the answer of 0. So if I just write the definition, or just write the name, additive inverse, it's sort of self-explanatory. So additive, we're summing the two numbers together, right? Or adding them together. And the inverse, well, if it's a positive number, the inverse would be negative. And if it's a negative number, the inverse is positive. So that kind of describes the definition there. It gives the example, oops. Whoops. Example of 7 plus negative 7. So we have the positive, I guess, version of the number and the negative polarity of the number. And when you add them together, you always get 0, right? So that shows you that if you have 7, the additive inverse is negative 7, and you will always have the result of 0. Okay. Let's go to solution. Okay. And the solution is correct. We can move on to the next question. Okay, question number 2. So this question asks, why are supplementary angles important? So I guess first we can go over what a supplementary angle is, right? So say we have two angles. So something like this. We have our angle alpha and our angle beta. If alpha is our given angle, for example, or angle of interest, then beta would be called the supplementary angle. Supplementary angle. Okay? And that is because alpha plus beta, our supplementary angle, is equal to 180. So 180 would be going from this line here to this line, right? Because 180 is just a straight line. So supplementary angle is whatever you need to add to alpha to get to 180 degrees. So I'm just going to read the explanation here. So supplementary angles are important because its definition helps find the value of another angle. So for example, if you want to find what alpha is, and you're given beta, you can figure out what alpha is. So if, for example, we have 60-degree angle, if alpha is 160 degrees, we have an angle like this, and this angle here, beta, is 160. We want to figure out what alpha is, and it's unknown. We can easily use the supplementary angle beta and take 180 degrees minus beta, or 180 degrees minus 160 degrees, and it will tell you that alpha is equal to 20 degrees, right? This is alpha. because if you rearrange this equation here, you have 180 minus beta is equal to alpha, right? So that's why they're useful and important, because they can help you find this smaller angle, the complementary angle, the supplementary angle. Okay. So the solution is correct. Oops. There we go. And we can move on to the next. Okay. Next question. Question 3 is asking what the surface area of a cylinder is. Okay, so we have a cylinder. It's like this. So that's shape that has a radius of r and a height of h. Okay, so a cylinder would be a circular. It's kind of like a tube or something like that. It's circular, but it has a top and a bottom. Okay, so the surface area would include the area of the top, the area of the bottom or the base, and the area of the lateral surface, or the surface all the way around the tube, right? So we want an area of a cylinder. We have to add together a surface area of the top, the surface area of the base, and zoom out a little bit, and the surface area of the lateral surface. Oops, lateral. Okay, and since the top and the bottom are the same, we can write 2 times the base plus the area of the lateral surface. Okay, so now we have to figure out what the area of the base and the area of the lateral surface is. So let's start with the base. So as you can see from my diagram, the area of the base is just a circle, right, with a radius r. So we can say area of base is equal to the area of a circle. And we know that the area of a circle is pi r squared. Okay? So next we need to figure out what the area of the lateral surface is. So lateral surface. So if we imagine this cylinder without the top and bottom. See if I can draw it, okay. Kind of like a hollow tube, right? If there is no top and bottom, we can imagine sort of unrolling this shape. And when we unroll it, we should be able to get a rectangle, right? So rectangles, in order to find the area of the rectangle, so we'll say area of the lateral is equal to the area of the rectangle. So yeah, imagine unrolling it and you have the same, it's the same area, just on a flat surface, right? So when we find the area of a rectangle, we usually do length times width, right? So if we have length here, well, we know it's height, as we saw previously that the height of the cylinder is h, and so the width of this rectangle is the same thing as the circumference. It's just the same, just unrolled, right? So the circumference of a circle, I'll say C for circumference of, oops, I can't spell circle, is equal to 2 pi r, right? So if we have length and width, we know length is the height and width is 2 pi r, as we determined up here. Okay, and that gives us the area of the lateral surface. So now all we have to do is go back up here and add them together to get the total area of the cylinder. Okay, so area of the cylinder is equal to 2 times the area of the base, because remember we have to account for the top and the bottom of the cylinder, plus the area of lateral surface. So 2 times area of the base, which we determined to be this, pi r squared, plus the area of the lateral surface, which is h2 pi r. Obviously, you can rearrange that. And if we factor out 2 pi and r, we get 2 pi r plus h as the area of the cylinder. That's the final answer. And I can also show an example, as they do here. They give us this cylinder. So let's look at that example. So from this diagram, we can see that the radius is equal to 4 inches, and the height appears to be 8 inches, right? So let's try to solve what the area is from the formula we just found out. So we have 2 pi r, which is 4 inches, and then r, which is 4 inches, plus h, which is 8 inches. Okay. 2 pi, well, we can multiply the 2 and the 4 there, so that's 8 inches times pi, and then 4 plus 8, we have 12 inches. Okay, and then we have inches times inches, so the final answer would be 96 pi inches squared, right? And obviously you can multiply the 96 times pi to get like an exact answer, but, or sorry, like an approximate answer, but since pi is repeating, we'll leave it as this for an exact answer. And yeah, that's how you would apply the formula we just found out. Okay. And that's all for that question. So, example number 4. So this example asks, well, it doesn't really have a question, but we're going to say it's asking about Intrusion angles, and I guess we're going to describe what exactly they are, right? So, Intrusion angles, they're basically two angles, or two, here, I'll draw what they have here, right? We have one angle that has 30 degrees, one angle between two lines or rays or vectors or whatever line sort of structures you have. And then you also have another one, right? That is a little bit different. It's maybe a little bit, the lines are different, the lines are different lengths, the orientation is different, right? But in this case, these two angles are considered Intrusion angles, right? Intrusion angles. So a Intrusion angle is basically just two, or just an angle, two angles that have the same measurement or magnitude, so they're both 30 degrees, but they do not have to have the same ray or vector or line lengths, and the orientation of these two angles. As you can see, that the two lines for the first one are like this direction, the other one's flipped, so it doesn't matter what orientation they are considered contrusion angles. Okay. So looking at the solution, these two angles have a different orientation in different directions, but since they have the same magnitude or same value, then their angles are contrugent. So, yep, as long as the magnitude of the angles are the same, therefore they are contrugent. It's kind of repeating the same thing over, but hopefully that makes sense. Okay, example number 5. Whoops. So we're looking to find the integral of exponent or exponential, sorry, to the power of x times sine x. Okay, so let's write that. We'll have the integral of e to the x times sine x dx, right? Okay, so what we're going to do for this problem is we're going to use IBP or integration by parts. So let's write what that is. Integration by parts, lines, parts, or sometimes people call it IBP. Okay, so integration by parts. Let's see, that's if you have u dv, you can rewrite this as u times v minus the integral of v times du. And sometimes this is done because it's easier to take the integral of v than it is to take the integral of u. So we're just rewriting it so it might be easier to compute. All right, so let's try to apply this to what we have. So what we're going to do is we're going to designate some values as u and some values as v so we can replicate this integration by parts formula. All right, so let's let e to the power of x equal to u, and let's let sine x dv, or sorry, dx equal to dv. Okay? So I kind of wrote them backwards because it's not the way that you're used to seeing it, but if we take the derivative of this first term here, the u term, let's do du by dx. Well, what's the derivative of e to the power of x? Well, e to the power of x, it's always just the same since x is, there's nothing in the exponential, it's just x. So the derivative of the exponential is just itself. What we're going to do here is move the dx to the other side. And you'll see why when we have to substitute it in the equation for the integral above. So yeah, move that to the other side, and that's ready to use for IBP. So for this sine x dx term, for the exponential term that we just did, we took the derivative. But for the sine x term, we're going to take the integral so that we can see what the non-integrated version looks like, okay? So we're taking the integral of both sides. We know that the integral of sine x dx is negative cosine x plus c, some constant, and that is equal to v because the integral of dv is just v, okay? So this constant here, I'm just going to leave out for now, out of the equation when I sub it in. You'll see in a second. I'm just going to leave that out because we're going to add it in later. It might get in the way, so a little bit confusing if you leave it in, but we definitely have to make sure to include it later. Okay, you'll see what I mean in a second. So let's sub things in for integrating by parts. Okay, so starting from the same first equation, we have e to the x times sine x dx. Okay, let's, if that is the u by dv portion, then let's write what u times v is. So u is e to the x. I'm just going to underline things as I go, okay? So e to the x is u times v. This is v. We have minus cos x plus c, which I said we're going to leave out for now. How much am I blocking here? Oh, just the IVP. Okay. And then, zooming out a little bit, we have minus the integral of v. V we just saw is minus cos x times du. Okay, du we calculated to be e to the x dx. All right, so now you kind of understand why I needed to take the derivative and why I needed to take the integral, right? Because they were useful when we were subbing them in for integration by parts. Okay, so now that we have this, I'm just going to simplify it slightly so that we get rid of all these brackets. I just left them there so you could see which parts were u and which parts were v, but we don't need them right now. So actually the minus cancels out, so we have plus the integral of cos x e to the x dx. Okay, so now you can kind of see, well, we're kind of back to square one, right? We still don't know what the integral of cos x e to the power of x is. It's kind of almost the same thing as what we had originally. So that means what we're going to have to do is apply integration by parts again. All right, so I'm going to do the same thing as first time, and we're going to let u equal to something else now. So we're just focusing on this portion, right? Because this first term is now integrated. We don't have to worry about it anymore. We're just working with the second term, okay? So we're going to let u equal to the same thing as before, e to the x, so this term here, and we're grouping the cos x and the dx, even though they're not next to each other. We're going to group those together, right, for dv. dv, is equal to cos x dx. Okay. So we're going to do the same thing as we did before. We took the derivative of du by dx equal sign equals to e to the x, because remember the derivative of the exponential function is just itself, and we're just going to move that dx over again, really just the same as last time. And for the dv term, the cos x dx, we're going to integrate again. So we get v is equal to, well, the integral of cos x is sine x. And we have a plus c term. Like I said, leaving that out for now, but we will come back to that and add that in later. All right, so now we can sub it back into for this part above. Let me write the whole thing again. So we have x sine x dx is equal to minus cos x, because remember the first term stays the same because we're done integrating, with that. But we have this whole second term that we need to write. So we have plus, okay. So now applying integration by parts. It's all the way up there. Hopefully you can still see that. Okay, so if we have u times dv, we're going to have u times v out in front. So u is e to the x times v, just sine x in this case. Remember, just leave out the plus c for later, unless you want to keep that in. That's up to you. And then the integral of v, that's the sine x. Running out of room here, right in the corner. Hopefully that's still clear. At times, where are we? Times du. Okay, du was e to the x dx. All right, close that big bracket there. Okay, now we're going to just simplify and well, why did I change that? Here we go. Minus cos x e to the x plus, I'm just rewriting without all these extra brackets so that it's easy to see, minus sine x. Well, actually, I'm going to change the order of this. So we have minus exponential x times sine x dx. Well, if you notice, you actually have something pretty cool here. We have this term and this term, which is the same term on both sides of the equation. Now this one's being subtracted, this one's being added, so we can't cancel them out. But what we can do is we can move this term on the right hand side of the equation to the other side of the equation, right? So we can do that just by adding them, or adding this term to both sides. So that's what I'm going to do. And when you add this term to the other side, you actually get 2 times the integral of e to the x times sine x dx. And then the minus cos x e to the x plus e to the x sine x. And there we go. So as you can see, on the left-hand side, we have the integral that we are trying to figure out. And on the right-hand side, we don't have any more integrals. So it's a solution, right? So let's divide both sides by 2. The whole thing there is divided by 2. So we get that the integral of e to the x sine x dx is equal to minus cos x e to the x divided by 2 plus e to the x sine x divided by 2. Okay, and we can't forget our plus c from before. That's the only thing. I didn't include it before up here. Oops, sorry, too far. I didn't include it here when I added it into the equation. I didn't include it in the second step when I added it to the equation. I didn't want it to get in the way, but if we did add it, we would have had to add it to the right-hand side of the equation. So I'm just adding that in now, the plus c. And remember this constant, this plus c, it can be added or divided by 2 or anything like that, and it's still c, it's still a constant, right? Because a constant divided by 2 is still a constant number, okay? So, yep, don't forget to add that, either if you want to add it in before or add it in at the end. And this is our final answer. So might be kind of an unexpected way to get to this answer, but that's how you do it. So that's how we found the integral of that equation. So these are the answers. Just going to put this solution is correct, and we can compare to see that it's the same thing. I just have the cos and the exponential swapped, right? All right, that's it. Okay, for question number 6, we're asked, how do you find a diameter from the circumference of a circle? All right, so we have, oops, moving around. We have a circle, not a very good one, but we have a circle, and and this circle has a diameter d, right? So the distance from one side of the circle to the other through the middle. We know that the diameter is the same thing as 2 times the radius. So if you split that down the middle in half, you have diameter is equal to 2 times the radius. Radius is from the center of the circle to the edge. The distance from the center of the circle to the edge, okay? And we also know that the circumference of a circle is equal to 2 pi r. Well, if you rewrite that as pi 2r, right? Well, we know that 2r is the diameter, pi times d. You might also see the circumference given in this form too, and that's also correct. So if you want to find out what the diameter is from the circumference, right, all you have to do is rearrange this equation. You have circumference is equal to pi times diameter. Well, if we want to rearrange for diameter, we have c divided by pi. And that's how you find the diameter from a circumference of a circle. So if you're given the circumference, then that's all you need because you divide by pi, which we know is 3.14, 16, etc. It's a long number, but when you plug it into your calculator, you can find it there. All right. And we are done. Okay, that's all we're going to be covering for today. If you did find this helpful, please leave a like, and if you want to be notified of when we do another Q&A like this, please hit the subscribe button and the notification bell. If you want to submit any of your own questions, you can see the links in the description below, or leave a comment, and that would be all for today. Thank you for watching.